Hey guys, so today we have a pressure equilibrium problem, and the question states, what is the equilibrium constant for the reaction that we have up here if zero point 0.5 mole of PCl5 is removed? And also, what would be the pressures of each species in equilibrium? So, things to first know would be that the equilibrium mixture is at 345 Kelvin in a 6.5 liter vessel. Also, our concentrations for each of the species is 1.35 mole of PCl3, 0.45 mole of Cl2, 3.2 mole of PCl5. So, and our our equilibrium constant pressure is 1.21. So, since this is a pressure problem and not a chemical equilibrium problem, we're going to have to find the pressures. So, in order to do that, we're going to have to use our good old friend PV equals nRT. And let's start off with the first species. Let's do that. So for PCO3, we have 1.35 times our R, which is a constant, which will be given to you in most exams. 345 Kelvin. This is always in Kelvin. Over 6.5 liter, which will give us 5.08 atmosphere for pressure for PCl3. Now we're going to find for Cl2. So, see that there. Cl2 equals P 0.45 mole times 0.08206 times 345 Kelvin, all over the 6.5 liter, which is our V. If we solve for P, will be P equals nRT over P. We will get CO2 equals 1.96. That's for CO2. Now, for our PCO5, which also in the question states, what is the equilibrium constant for the reaction if 0.5 mole of PCO5 is removed? So, what we're going to do for this one here is when we put in our N in our PV/nRT equation, 3.2, we're going to minus that from 0.05 mole times our 0.08206 times 345 Kelvin, all over 6.5 liters. And for PCl5, what we'll get is 11.8 atmospheres. So, now that we have all of our pressures, what we're going to do now is plug all of these in to our ice table, which I have already set up. So we'll write this in. 1.96 goes to 11.8. Okay. 18. Also, in this problem, if you set up the Q equals, in order to find out which way the reaction goes, we would have to set up the Q, so we'll use the molarities, which will just be products over reactants, which would be 3.2 moles over 1.35 times 0.450. And here you'll get a number greater than K, so you'll get. And also what I like to set up in these problems is a table, and for the K, I put 2 K's, one greater than, one less than, put Q in, and I put a line through here. So the one greater than Q will be forward reaction, and the one less, the K less than Q will be the reverse action, reverse order. So we know here we'll get a number, and this will be greater than obviously 1.21. So it would be going in the reverse order because it's greater than the K. So what we'll have here is minus x plus x. Plus x. And here we'll have 5.88 minus x, 1.96 minus x, and we'll have 11.8 plus x. So what we can do here is use these equilibriums to plug into our K formula, which will be our K equilibrium pressure equals 1.21 equals, which will be the reactant plus x over our products. Product x. So when we distribute this all out and put it in a standard form, we will use the quadratic formula. So after you use the quadratic formula, you use the distributive properties, and then you'll use the quadratic formula to solve for x, and you'll get an x value of about x equals 0.210, I believe. So what we're going to do with this, and this is to find out all the pressures of each species in equilibrium. So we'll use this here, and we'll plug this back into these equations. So we'll get 5.67. And that will be our individual pressures. And there you have it.